Yesterday we have seen how to do level process control experiment. Today let us see how to do experiment on flow process. Tuning, this is second experiment. Tuning and the closed loop control of flow process. There is no mathematical modeling. Tuning and the closed loop control of flow process. Flow process, already we have seen. Here, this pump is the flow process. Pump and valve, if you consider this part alone, what are all there? Pump, rotameter, valve, that's all. If you consider this part, then it is called flow process. Here we are going to control flow rate. Flow rate of the process. So this is a pipeline. And that flow rate has to be controlled. For that, you can put a valve here. You can adjust that valve. For that, you have to measure the flow rate. For that, orifice meter will be there. I think you studied orifice meter. Orifice you studied. By using that, you can take tappings across the orifice meter, and it should be given to DPT, differential pressure transmitter. It gives 4 to 20 milliamps. That is given to controller, PID controller. The output of the PI controller is given to I to P. Here, the output of the PI controller is 4 to 20 milliamps again. The output of I to P is 3 to 15 psi. That is given as input to the valve. So we are measuring the flow rate through this tube. It is compared with the set point. PV is compared with set point. If any error is there, the PI will manipulate the manipulated variable. So it can be controlled. This is a kind of flow process. The flow rate through this tube can be controlled. Before this, a pump will be there. That and all may not mentioned here. The problem here is, if you put a valve, what is happening is, suppose always I want to control 50% flow rate, means the valve is always closed to 50%. Suppose the valve is opened 100%, means the flow rate will be 100%. Am I correct or not? But the pump here, the pump before, the pump will be here. This pump has to always try to pump 100%. How it is reduced to 50%? Because the valve blocks 50%. Otherwise, 100% flow rate will be there. So the energy is dissipated across the valve by pressure drop. Because of pressure drop, because of the resistance of this valve, the flow rate is reduced because of resistance. If you put resistance, the energy is lost. So the pump always tries to pump 100%, but because of the valve 50% only, that's why energy loss. Here we'll use half HP, 1 HP, like that. In industries, it may be 5 HP, 10 HP, even 100 HP. 100 HP pump means, suppose you are using only 50% flow rate only, means you are wasting the 50% energy. Suppose in the industry, let us assume that 5 HP motor is some 10 flow process are there. Total power how much? 50. 5 multiplied by 10, 50 HP. So 50 HP power, only you are using 25 HP power. The remaining 25 H is energy is dropped across the valve as waste of energy. So that's why this valve can be replaced by variable speed pump. Variable speed pump. That we will see now. So instead of having the valve, we can use variable speed pump. We are measuring the flow rate through DPT. Differential pressure transmitter measure the flow rate. It is connected to this pump. This is the pump. Pump is coupled with a motor. 3-phase induction motor. So this differential pressure transmitter gives 4 to 20 milliamps flow rate, 0 to 100% flow rate. If no flow rate, 4 milliamps, 100% flow rate, 20 milliamps. So it gives, that is given as input to the PID controller. Set point is given to the PID controller. So the summing block I am not mentioning here. So summing block is inside the PID controller. So the output is again 4 to 20 milliamps. Instead of using valve, we can put one device that is called VFD, variable frequency drive. Variable frequency drive. If we give 4 to 20 milliamps and power supply to this, single phase or 3-phase depends upon the design. Here in our lab, we have single phase 230 volt input, power input to this VFD. If we give 4 to 20 milliamps, it will give the output RYB, 3-phase output, RYB, 3-phase output, 440 volt, but frequency is varied from 0 to 60 hertz. Frequency is variable frequency drive. That's why it is called VFD. Voltage is constant, but frequency can be varied from 0 to 60. If you give 4 milliamps, frequency is 0. If you give 20 milliamps, frequency will be 60 hertz. This variable frequency is given to 3-phase induction motor. The speed of the induction motor N is proportional to 120 F by P. N is proportional to 120 F by P. P is number of poles in that induction motor. 120 is constant. That's why if you vary F, speed can be varied. So by varying the speed, we can vary the flow rate instead of putting a valve. That is the advantage of having VFD. If you put like this, you can save 50% of the industrial power. Instead of using valve, if you put the variable frequency drive, 50% of the power will be saved. So suppose an industry has a power bill of 2 lakhs per month, means 1 lakh you can save. 1 lakh you can save. So 50% of the power can be saved if you use VFD. In our lab, we have this type of arrangement. We have this type of arrangement, not valve. But in level process, we have valve. There also we can put VFD. There also we can put VFD. This arrangement can be implemented in level process also. But in most of the industries, they will use valve. Nowadays, it is gradually changing to VFD. Okay, so this arrangement is there. So the flow rate through this pipe can be varied. It depends upon by adjusting this 4 to 20 milliamps. If you vary this 4 to 20 milliamps, the speed of the induction motor varies from 0 to 100%. 100% means full flow rate, 100% flow rate. No, 0 means frequency 0 means it won't run. That's why 0 flow rate. So you can vary the flow rate from 0 to 100%. by adjusting the 4 to 20 milliamps input to the VFD. VFD is a power electronic device. It will convert the given power into three-phase supply with variable frequency. Here, what you are getting is constant frequency power supply. The frequency is 50 hertz constant. That's why if you connect an induction motor, it will run at a constant speed, single speed. But if load, because of load, it may small change in the speed may be there, but you cannot vary the speed much. If you vary the frequency, you can vary the speed. That's why we can vary the flow rate. So this is the arrangement that you are having in the lab. So here, this is the pump, three-phase, coupled with three-phase motor. This is three-phase motor. Three-phase motor coupled with the pump. Coupled with the pump. So it depends upon the speed of the motor. Flow rate will be taken from the sump, delivered to this pipeline. It goes through this way, and again it comes to the sump. So this way the flow rate is there. You have to measure the flow rate. If you want to control the flow rate means how many liters per hour. If you want to control means you have to measure the flow rate. You have to measure the flow rate. You have to measure the flow rate. So there is a orifice meter. O. Orifice meter means it is a plate with a small diameter, smaller diameter than the pipe. That's all. Orifice plate is placed there. If diameter is reduced, there will be a pressure drop. By measuring the pressure drop, we can measure the flow rate. That is the idea behind that orifice plate. So across orifice plate, here low pressure, this side high pressure. Both tappings will be taken and given to DPT. Differential pressure transmitter. It is given to that. DPT gives 4 to 20 milliamps. Again, it is two-wire transmitter. That's why a 24 volt power supply. You can give from 12 volt to 24 volt. A 24 volt power supply is there. That is in series with the DP transmitter and the 250 ohm resistor. That's all. So that the across 250 ohm resistor, the voltage will be the potential drop, voltage drop across the resistor is 1 to 5 volt. So this PID controller is configured such a way that 1 to 5 volt will be taken as 0 to 100% flow rate. This is the PID controller. This is the PID controller. PID controller you can configure like your mobile phone. You can configure any type of input. You can configure for 0 to 10 volt, you can configure for 1 to 5 volt, or you can configure for 0 to 5 volt, or you can configure for the output of RTD can be directly connected, output of thermocouple can be directly connected, or you can configure for 420 milliamps like that. So it is configured for 1 to 5 volt. That's why the drop across 250 ohm is given as input to the PID controller. Set point is given as number. The PID controller in turn gives out its output 4 to 20 milliamps. 4 to 20 milliamps. 4 to 20 milliamps as output it gives. That 420 milliamps is given to VFD, variable frequency drive. The variable frequency drive that we are using in the lab as single phase input. Power input is single phase, 220 volt single phase. That gives the output of 440 volt three phase RYB. The phase shift between each phase is 120 degree. So RYB it gives 440 volt, but with variable frequency. Frequency varied from 0 to 60 hertz. That is given as input to the motor. That is given as input to the motor. Therefore, the speed of the pump, speed of the motor, induction motor can be varied simply by varying 4 to 20 milliamps. That's all. If you vary 420 milliamps, speed of the pump will vary. speed of the motor will, induction motor will vary, so speed of pump will vary. That's all. This is the experimental setup. One more point I missed, that is the rotameter. Here also one local indicator is there that will indicate the flow rate. A rotameter. A float will be there, depends upon the flow rate. The float will go up and down. From that we can measure locally, we can measure the flow rate, but no use of control. Rotameter will not be useful for control purpose. It is for local indication. That's all. This is the experimental setup. Here we are going to use to do the flow process experiment. There are Ziegler-Nichols suggested two types of tuning. Yesterday we have seen one type of tuning, that is called the reaction curve method. Reaction curve method. How we obtained that reaction curve? Put the controller in manual mode, that is open loop. So it is an open loop experiment. Put the controller in manual mode, that is open loop. Bring the process to nominal operating point. Give small change, say 5%. You will get the response in open loop response. It will be S curve. It will be like S curve. That is called reaction curve. That is called reaction. Yesterday we have seen. You will get reaction curve. From that you will find Kp, Tp, Td. By using these three, we can find the tuning parameters. That is called open loop method. Open loop method. Another method is there, that is called closed loop method, that we are going to use here. Closed loop method can be used only in fast process. Level process, the time constant that we have seen about 3 minutes. The time constant that we have seen is about, I didn't remember. Do you remember the time? 20 seconds or minutes? 20 seconds. The time constant is 20 seconds. The process takes 20 minutes to settle. Time constant of the process is 20 seconds. But it takes long time to, because it is not first order. So fifth order, it takes long time to settle. Why it takes 20 minutes? Because it has dead time. That's why it takes long time to settle. But the flow process, theoretically the flow process is zero order process. Theoretically the flow process is zero order, not even first order. Theoretically, no process in the world is zero order, that we know. But mathematically, if you obtain from the first principle, if you obtain mathematically, it is zero order process. It is a fastest process among 4 processes: level, temperature, pressure, and the flow rate, flow process. If you consider all the 4 together, flow process is the fastest. Pressure and level are moderate. Temperature is slow process. That's why for temperature process only we will use derivative mode that we have seen. But we cannot use the closed loop method for temperature, pressure, and temperature flow level. For level, temperature, pressure, we cannot use closed loop method. We have to use reaction curve method to find the tuning parameters. So in level process, by using reaction curve, open loop method, we find the tuning parameters. But here we can use closed loop method. That's why the title is tuning and closed loop control of flow process. No mathematical model obtained by that we have obtained in level process. In the closed loop method, suppose this is the process. The closed loop, this is the process. Process means system. We are putting this in P only. P only. P only means only KC. P only process. Set point is given. Initially, we will put in a closed loop. That's all. Already I said it is not zero order, because what and all connected in series with that. Let us assume that the flow process is zero order. Mathematically, theoretically it is zero order. with that a DPT, that is another first order. Then in series with that a PID controller, another first order. In series with that VFD is there, another first order. So the motor is there, fifth order. If you consider motor and pump together, it can be first order. So there are 5 components in series, at least 4 orders, fourth order, because theoretically the flow process is 0 order. That's why the remaining 4, if you consider, is fourth order. Fourth order. So if you increase Kc, definitely it will become unstable unit. Because if it is fourth order means, let us have between these two, this will go like this, this will go like this. This is the root locus diagram. At a particular value of K max, K equal to Kc equal to K max, it will exhibit oscillation. If any further increase in Kc, it becomes unstable. It becomes unstable. So, by using that concept, we are going to tune here. If we go on increase Kc, the poles are moving from left-hand side to right-hand side. The pole is moving from left to right as Kc increases. As Kc increases, the pole is moving. At one value, at one point, it will exhibit sustained oscillation. At one point, it will exhibit sustained oscillation. Sustained oscillation means continuous oscillation. If any further increase, it becomes unstable. We have to find that point. So we are putting only proportional controller. We are going to increase Kc gradually. At one point, suppose I am giving 50% of K max, then what will happen? You are giving a set point of 50, the cross variable number is 40. That time you connected, therefore it will oscillate and finally it will settle. Finally it will settle at 50. Not 50, it may be settled at 45, 46. Because P only, steady state error will be there. But anyhow, the oscillation, damped oscillation. Say the Kc is, when Kc equal to 3, it exhibits sustained oscillation. Let's assume Kc equal to 3, K max equal to 3. You gave 1.5, that's why it is damped oscillation. Gradually, if you increase, this oscillation will increase and it damps out after a long time. If you increase. But after some time, the amplitude will decrease. Finally, it becomes 0. No oscillation. When Kc equal to 3, it exhibits sustained oscillation. No decrease in amplitude. Continuous oscillation. Means the poles are exactly on the JMAG axis. That point we have to find that Kc. That is called Kc max. K max you have to find. Let us assume that K max equal to 3. K max equal to 3. Let it be. We are assuming. What is that? K max equal to 3. And one more thing we have to find, that is the period of oscillation. Time taken for one oscillation, that is called TU. Period of oscillation, TU. That we have to measure. If you know K max and TU, this K max can also be called as KU, ultimate gain. KU and TU, if you know, you can find the tuning parameters. The tuning parameters are for P, PI, and PID. KC, TI, TD. Kc 0.5%, 0.5 times K max. no TI, no TD for proportional only control. It means what? The gain margin is 50. The gain margin is 2. If you increase twice the given K, then the system becomes unstable. Then the system becomes unstable. Therefore, the gain margin equal to 2. That way it is designed. For PI controller, it is 0.45 times K max. Further decrease in gain because we are going to introduce TI. TU by 1.2. TU by 1.2 times. No TD. We know the period of oscillation divided by 1.2 will give TI. That way we can find. For PID controller that we are not going to use anyhow, the formula is 0.6 times K max. Because our derivative mode we slightly increased. That and all we'll see why we are increasing. Why he increased the gain. That and all that we will see later. TU by 2, TU by 8. So these are the thumb rules to find the tuning parameters. But anyhow, it is fast process. That's why we won't use PID controller. For fast process, no need to use for fast process, no need to use derivative mode. Only proportional mode and integral mode will be used. PI or P will be used. So how to find, how to do the experiment that we will see now. So this method is called closed loop method of tuning. This method is called closed loop method of tuning or continuous cycling method. Another name for this method is continuous cycling, continuous oscillation. That's why it is called continuous cycling method. The third method is called sustained oscillation method. Closed loop method, sustained oscillation method, or continuous cycling method. All the three are same, one and the same. Now, how to do the experiment that we will see now. Connect the module as per loop diagram. So this two-wire transmitter has to be connected as per the diagram. So that 1 to 5 volt will be given to PID controller. That is the first step. Switch on, the pump will be turned on. Keep the controller in manual mode. Keep the controller in the manual mode. The MEIN signal will blink. It means it is in manual mode. Set the controller output equal to 100%. Set the controller output equal to 100%. Controller output will be 100% means you are giving 20 milliamps. The pump will, the induction motor will run at maximum speed. Induction motor will run at maximum speed. That time the flow rate must be 100%. You can adjust by hand valve. Already I told you that one hand valve will be there. Rotometer is there. You can see whether it gives 100% or not. So you have to fix that 100%. Let us say in the lab there may be some deviations that they will tell at the time of doing experiment. Because sometimes it may be turbulent from 80% to 100%. That's why they will restrict to 70% of motor speed. Motor speed, if you go beyond 70, that way turbulent. The DP transmitter will give constant value for laminar flow, not turbulent flow. The flow can be seen in two ways. One is turbulent flow. Turbulent flow means, you know, some bubbles will come. Turbulent flow rate will be very turbulent. DPT will not give correct value. For laminar flow only it will give. Up to 70% it gives laminar flow. That's why for 70% the flow rate will be made at 100%. These are all some adjustments that we are doing for better response. So I am not going to tell all those things. That will you learn in the lab. Keep the controller in manual mode and the controller output made 100%. Then adjust the flow rate. The maximum flow rate is 10 gallons per minute. 10 gallons per minute. The LPH also will be there. I think some 12 or 15 liters per minute, I think so. That you have to fix 100%. That is equal to 100%. That's all. 100% flow rate you fix for 70%, for 100% controller output. Now put the PID controller in P only mode because if you want to exhibit sustained oscillation, only KC must be there, no TI. That's why we have to put the controller in P only mode. How to put the controller in P only mode? Here, TI equal to 0, you should not put. Because 1 by TI, actually in the formula, what is there? 1 by TI. 1 by 0 will what? What will happen? Divide by 0 error you will get in a microcontroller. That's why you should not enter 0. So 1 by TI, how we can eliminate this? We have to enter infinity, because 1 by infinity equal to 0. Infinity you cannot enter in a controller. That's why enter the maximum possible number, 9999. Or in some controllers, there will be a provision to turn off. I think there is a provision to turn off in that controller. It's there. And the more controller. There is no provision to turn off the TAP mode. That's why we have to enter 49. 49 means it is negligible. 1 by almost 10,000. 49 means 1 by 10,000. Negligible. So TI becomes negligible. Here it is in PB. Yesterday I said the controller that you are using in terms of PB, not in KC. So we have to put PB equal to what? 100 by KC. You put PB equal to 100 means KC equal to 1. From 1 we will increase gradually. If you decrease KC, if you want to increase KC, what will happen? PB will decrease. If you decrease KC, PB will increase. So what we have to do is, we have to decrease PB, means we are increasing KC. We have to decrease PB from say 200 or 300. Initially give 200. It's not 100%. You should give some 200%. Say 200. Initially give 200%. It means you are giving KC equal to 0.5. 100 by 200 equal to how much? KC equal to 0.5 initially give. If you want to increase KC, means you have to decrease PB. From 200, gradually decrease PB. So you are moving the pole towards J omega axis. You are moving the pole towards J omega axis. You are moving the pole towards J omega axis. At one point, it will exhibit sustained oscillation. It will exhibit sustained oscillation. How to see the oscillation here? To see the oscillation, the rotameter, a float will be there. A float is there to indicate the flow rate. A float will be there. A truncated bob will be there. That will indicate the flow rate. That will go up and down. Sustained oscillation means what? Flow rate increases, decreases, increases, decreases, increases, decreases. Theoretically speaking, it goes up to 100% and goes to 0%. But practically it is not so. But it will increase and decrease. So increase means the bob will go up. Decrease means the bob will go down. So the sustained oscillation means this rotameter bob will go up and down. It will go up and down. How to say it is sustained oscillation or not? Damped oscillation. Sustained oscillation means, suppose the maximum flow rate is 8 LPM. Let us assume 8 LPM. Lower value is 2 LPM. Again and again, it goes to 8 LPM means it is sustained oscillation. Some first 5 times it goes up to 8 LPM. After 5 times it goes up to 6 LPM. After that it goes to 5 LPM means after some time it may settle. It may settle. It goes like this. It goes like this. Finally it will settle. So it is not sustained oscillation. The poles are not on the J omega axis. Goes to 8 LPM and 2 PLM continuously means that is called sustained oscillation. Till then you have to decrease PB. At one point, it will exhibit sustained oscillation. At one point, it will exhibit sustained oscillation. Note down that is called PB min. PB min. KC max or PB min. They are inversely proportional. That's why we are talking it in terms of PB min. So now I got PB min. How to find the period of oscillation? Time taken for one oscillation is period of oscillation. One time bob from top to bottom, then again come to top, one oscillation. So how to measure? If we measure for one oscillation, it may be 9 seconds, maybe 9 seconds, 7 or 8, 9 seconds it may be. 9 seconds, measuring 9 seconds is very difficult. That's why we'll measure for 10 oscillations. We'll measure for 10 oscillations. First time when it starts to come down means that time we'll turn on the timer. For 10 oscillations, we'll measure the time, divide by 10 because error will be minimum. Error will be minimum. So you will get the period of oscillation, TU, in terms of seconds you will get TU. So you measure both. Now K is K max, that is PB min. It exhibits sustained oscillation. So TU also you got, PB also you got. Now we can use the formula to find the tuning parameters. Already I told you that the tuning parameters for this is 0.5 times K max. PB min if you use, then PB min divided by 0.5. So the KC means we have to multiply. PB means we have to divide. So this is for P controller. For PI controller, what we have to PB min divided by 0.45. We have to find a TI. This is PB. TI, no TI for P only controller. For PI controller, TI equal to the period you found, ultimate period divided by 1.2. So you got the tuning parameters. Now we have to do the experiment. First thing is we have to obtain servo response. So you have to enter the tuning parameters, bring the manual mode. You continuously press the escape while it displays set point. It will get into that mode. Configuration mode, enter PB, TI, then come out. If you continuously press escape, it will come out. It is in manual mode. The flow rate you gave 50%. That's why let us assume that flow rate is, you gave controller output is 50%, flow rate also 50%, let us assume. So make set point equal to PV. Make set point equal to PV and transfer from manual mode to auto mode. It will settle at 50 quickly. No need to do bumpless transfer because very fast process. If any deviation is there, it will take care. Immediately it will settle at 50%. Now, if we change the set point from 50 to 55 or 50 to 45, immediately it will change. Now let us assume that it is in 50%. At this point, I am changing the set point to 55%. That's why this will change like this. And finally, it will settle at 55. So that is called servo response. That is called servo response. This is called servo response. Whether the controller works for change in set point, we are checking. Yes, it is called servo response. Regulatory response, again change to 50, it will come. Again, if we change it to 50 means, you change the set point to 50 means, again it will come down. Again, it will come down and oscillate and finally it will settle. Now it is settled at 50. That time, you give small change in flow rate. Give small change in flow rate by adjusting hand valve, not adjusting the controller out. Hand valve, if it's slightly close or open, flow rate will be modified. So flow rate is 50%. Because of the disturbance, it goes up. But the controller takes appropriate action and again it brings back to 50. That is called rejection of disturbance. Rejection of disturbance. This is called regulatory response. This is called a regulatory response. Suppose two controllers are there. If you want to find the performance of two controllers, one controller using different tuning parameters, another controller different tuning parameters. Two controller means here Both are PI controller. For one controller, you are putting less proportional value. Another controller, you are having higher proportional value. TI same, let us assume. In that case, which gives better performance? How to measure which quickly settles? That is the better controller. You understand that? One controller settles quickly to the set point means that is better controller. How this is qualitative analysis. What I'm saying is quickly settles. That's why it is better. I'm saying means that is qualitative analysis. Quantitative analysis is there. How to measure which settles quickly? That is called ISE-IAE. ISE-IAE. I do not know for flow process you can't do. For level process you can do. You are taking readings. No, flow process very fast. That's why you cannot take readings. Cannot take readings. You can note down settling time and you can draw the rough graph. That's all. Cannot take. If it is automatically it is recorded in PC, you can take the data and you can draw. Otherwise, it's not possible. Very fast, you know. That's why it is not possible. But for level process, you can find ISE-IAE. You are getting, you know the set point, you know the PV. Set point is 50. PV is initially it is at 40. Set point is continuously 50. It goes to 47, 48, then 51, 52. Then again comes to 49. Finally, it settles at 50 means you can find error. You can find error. The difference between the two is error. Integral means summation. Integral square error means square all this error and add. You will get some quantitative. You are quantitating the performance. That is called IESE. For two controllers, for two different controllers, you are finding ISE means which settles quickly will give less ISE. Which settles quickly will give less ISE. So you have to find E square and add, you will get ISE. Find the modulus value, modulus of U and add, you will get IAE. Integral of absolute error. This is integral of square of error. You can compare the performance by using that for level process, not for flow process. Since it is very fast, you have to automate recording of data, then only it is possible. Otherwise, it's not possible. These and all already, the controller operation already we have seen. The controller operation is, there will be 4 buttons. One is called escape, left hand side, right hand side is called the enter key. Enter key, this is escape. The middle two are increase decrease buttons. You can increase decrease in manual mode only. How to transfer from manual? There are 2 displays here, set point as well as manipulated variable. You can toggle between the 2 by pressing escape key. If O is display, if you continuously press enter key, it will transfer to auto mode. When set point is displaying, if you continuously press escape, it will go to configuration mode. This displays the process variable in terms of percentage. So that's all about flow process. That's all about flow process. The next one is how to control, how to simulate servo and regulatory response of a soft process. Since it is soft process, you can do both type of tuning, reaction curve method as well as sustained oscillation method or closed loop method. Both can be done in soft process. You are taking a 4th order soft process. For that you can do experiment in MATLAB simulation. In MATLAB simulation, that is the 3rd experiment. The 4th one is control valve characteristics. The control valve design, there are 3 types of design that we are going to see. 3 types of design. One is quick opening, equal percentage, and linear valve. You are designing a valve which behaves like a linear valve. If you install, it becomes non-linear. That's why to know about that, I'll explain the next class, control valve characteristics. And the final 5th experiment is configuring a PID controller. In PID controller, very small device, it has hundreds of parameters inside. We are adjusting only KC and TA. Other parameters we are not considering. So to learn more about the PID controller, the PID controller alone is given to you. You will be asked to give simulated PV, simulated set point. For that, what is the controller output? Theoretically, you will calculate and check what is the controller output. To study the behavior of PID controller, that experiment is the 5th experiment, configuring PID controller. These are the 5 experiments. The other 3 we will see in the next class.